All right, welcome back to Math Ninja videos. Today we're going to be talking about linear regressions, which is a big word for a pretty simple concept. All right, so in today's lesson, we're going to be dealing a lot about XY coordinates, right? Some data that can be represented by XY coordinates, right? And what we're going to do is say if I took those XY coordinates and I graphed them, right, on a coordinate plane, right? What a linear regression will do is it'll try to take that data and try to make the best straight line that it can, the best linear equation it can with that data. So if, just doing it eyeball, it would be some kind of graph like this where, some of it's below it, some of it's above it, there's a little bit of data above it, there's a little bit of data below it, and then it's going to try to take that data and try to make the best y equals mx plus b for that. So that's really all linear regression is, right? It's going to take data and try to make the best line out of it. All right. It won't be a perfect line, but it will be a good line. All right. When you do these, let's first talk about an Inspire. You can do these on lots of other calculators, but an Inspire is the way I'm going to teach you how to do a linear regression. To actually sit and do the math yourself for a linear regression is actually somewhat complicated. All right. Uh, but the calculator will do the work for you. So when you do linear regressions, you probably need some kind of calculator that will, calculate the linear regression for you. All right, to do a linear regression, once you're on a scratch pad or any open document, go to Menu, Statistics, Stat Calculate, and then you're going to notice there's lots of things here: linear regression, quadratic regression, cubic, quartic, power, exponential regression. These are all different types of regressions. Trying to make lines that fit it best. You're going to hear me say the line of best fit. That's basically saying the line that fits the most data. Okay, or fits the data best. So we are going to deal with linear regressions, number 3. So let's go back a couple steps. The way you get here, you're going to hear me say this a lot, is Menu, 6 for statistics, right? 1 for stat calculate, and then number 3 we'll do y equals mx plus b, right? 3. Once you do that, it's going to open up this data here, right? In this place, you're going to type your x coordinates, and here you're going to type your y coordinates. Now, one thing to keep in mind is this piece of data right here. You see this? Um, blue bracket that we have here? There's parentheses down here, but right here there's a blue bracket. We are going to be using this bracket. Anytime you put a group of data in at a time, that's called a set, right? We're going to put a set of data in at the same time. Anytime you put a set in, like a group of numbers, you need to open up a set and see. Notice what happened here. Now I have a bracket, and then I'm going to type in my x coordinates, right? So let's say my x coordinates were 2 and 4, right? So, if I was looking at a graph and I had 2 points, let me get a pen here. If I had 2 points, right? 2 made 2 and 4 for x. And let's say when x was 2, y was, let's say, 7. And when x was 4, y was, I don't know what, -3, right? So when x was 2, y was 7. And when x was 4, y was -3. So you're going to put the x coordinates in first, the 2 and the 4. Then you're going to open up another set, control parenthesis, right, which is bracket. So we used 2, 4, and we used what? 7 and -3. 7, comma, -3. And then you're going to scroll all the way down till you get to OK, right? You can hit Tab. If you hit Tab, it will take you through them, right? So keep hitting Tab, hit OK. And what it's going to do is take that data and try to make a line out of it. So there we go. It says if this was a line, the equation of that line would be m would be -5 and b would be 17. So what it's saying is the equation of the line is -5x plus 17. Okay? Now there's some other data here. All right? There's an r squared number, there's an r number. For tonight, you need to really focus in on this r number. All right? So there's 2 things to keep in mind. That r number is called the correlation coefficient. Big word for a very simple idea. All right. Well, not such a simple idea. All right. So here it is. there's a range of things that R value can be, right? This is the R value. And that R value can be anywhere from -1 to 1. The closer it is to either 1 or -1, the better the line is, right? So if I had some data and the dots were like this, right? And I said make a line and I made that, the R value, right, the correlation coefficient would not be very good, all right? The closer this number is to 1 or -1, the better it fits. The closer it is to -1, the closer it models a negative sloped equation, right? The closer it is to 1, the more it models a positive sloped equation. All right. 1 is bad. 0 is bad here, right? This has no correlation at all. It's basically saying the data does not make a straight line. You know, if you took a bunch of dots that were in a quadratic, you'll learn about quadratics later on, but a curved line like this, and you said try to make the best straight line out of it, it would try to do something like that, and it's not going to be very good. All right. But if you took 4 dots like this, so let me erase a few of these, right? And I said, hey, take those dots and make a line. Oh, okay, well, it would do something like this, right? Probably something like that. And that correlation coefficient, that R value, that R number, is going to be very close to 1 because it has a positive slope, right? And it's very close to a straight line. So that's what the correlation coefficient is. You're going to talk about that today. You're going to need to pay attention to it. So the way you find the correlation coefficient when when you're doing a menu 613, right, a linear regression, is you look at this R number. R is -1. So what does that mean? Well, it means since it is exactly -1, it's saying that data perfectly fits a straight line. That's what it's saying. Well, that makes sense, right? Because if I only had 2 dots, right? So let's just say I had 2 dots, right? 2 points. And I asked the calculator to find the best line it could make. Well, if it needed to find the best line that it could make, it would just connect the dots, right? It would just go straight through them and just connect the 2 dots. And so this R number, right? This R value, this correlation coefficient is going to be perfectly 1. When you only have 2 dots, the R value will always be 1. Okay? Now, when you start getting more points, you know, like if you got a point here and a point here, then that R value is going to start going down to like 0.95, you know, 0.85. It can keep going depending on how bad the data is off that line. Okay? 0.85 or -0.85 is our cutoff point. Anytime it's 0.85 or more, or -0.85 to -1, this is good fit, right? It means the data is modeled very nicely with a linear regression, all right? Like I said, if you try to take a quadratic, something that's curved like this, and say make a straight line out of it, the R value is going to be very close to 0. Because when it's getting close to 0, it's saying bad. It's not a good line. It's probably not a straight line. The data's not linear at all, okay? So there's 2 things there, right? One, I'm going to clear my calculator, doc B. One is menu 613. Inside there, you're going to open up a set. You're going to put the X values. You're going to open up another set. You're going to put the Y values. And then you're going to press OK. You're going to get an R number. You're going to look at that R number. Well, you're going to look at the equation, right? What the slope and the Y-intercept are. And then you're going to look at the R value to see how good that fits. All right. So what we're going to do now is we're going to take some actual data and we're going to do a linear regression on it. All right. This first half up here, this is just talking about everything I just summarized, right? So let's just really quick say it. When I say a linear regression, it's used to find the equation of a line that best fits the data. Another word for that is line of best fit. The correlation coefficient, the R value, measures how closely the equation models a straight line. The closer it is to 1 or -1, the better a fit. 0.85 or higher is a good fit. That's also true for the negative version of that, right? How do you do that? You do menu 6, 1, 3. Then you open up a set, put the X and Y values, press OK, you'll get the equation. All right. So let's do it with the problem. It says, the Olympics. Below is a table showing the number of gold medals won by the United States at the Winter Olympics during various years. All right. Find the linear regression for the number of gold medals as a function of the number of years since 1992. Right. So what we're going to do is we're going to try to find the line of best fit for this data here. Now, we did a previous lesson, we talked about functions, right? You want to write a regression of the number of gold medals as a function of the year since 1992, right? That's actually a typo since 1994. Yeah, I just made I just made these notes, and I can already see a typo. So I apologize for that. I kept changing these numbers, right? Let me fix this here. So change that to a 4 if you don't mind, right? So 1994. So 1994, that's going to be year 0. 1998 is going to be year 4 because that's 4 years later. 2002 is year 8 because that's 8 years later. 12, 16, and 20, right? Notice from 1994 to 2004, that's 20 years later. A couple neat things to look at. Notice that it's every 4 years. Yeah, because the Olympics in the recent past has been every 4 years, right? The Winter Olympics has been every 4 years. So this data just saying, and this I pulled this from actual data. In 1994, we won 6 gold medals in the Winter Olympics. 98, 6, 2002, 10, 2006, 10, and 14, we earned 9 medals, right? All right, so first question, what's the independent variable? Yeah, well, that's the years since 1994. What's the dependent variable? Number of gold medals. And remember, you can always go back to this. Let me erase this here. You can always go back to this sentence, right? It's a function of the number of years since 1994. You're putting number of years since 1994 in the machine, and it's spitting out the number of gold medals. Okay? All right. So that's what we need to do now. So we're going to have to do a linear regression for this, right? So I'm going to go menu, 6, 1, 3. I'm going to open up a set, and I'm going to go back and I'm going to look at my data, right? What was my x coordinates? 0, 4, 8, 12, 16, and 20. So I'm going to type that in. 0, 4, 8, 12, 16, 20. All right, I'm going to go back and check it to make sure I did everything right. Yeah, and then my y value is 6, 6, 10, 9, 9, 9, right? 6, 6, 10, 9, 9, 9. So I'm going to go there, open up another set in the y coordinates. 6, 6, 10, 9, 9, 9. Press OK. All right, I'm going to click OK. And there it is. That's the line, the linear regression for this and for these data points, right? The slope is about 0.16. We're always going to round to the nearest hundredth, right? So it's going to be 0.16x plus 6.5. So I'm going to write that first, and then I'm going to come back and talk about the correlation coefficient. 0.16, right, was the slope, right? 16 hundredths was the slope, and the y-intercept was 6.5, right? 6.5. All right, so the equation of the line was y equals 0.16x plus 6.5. And then it's asking, what's the correlation coefficient? Well, we go and we look at this right here, right? 0.71. So we're going to write that. 0.71. Now listen, what did we say earlier? Anything above 0.85 is good. So is this a good fit? It's an okay fit. It's not a good fit, right? So the data's kind of modeled by this, but it's not exactly modeled by it, okay? So it's not a perfect linear, it's not very linear is what it's saying. It's not horrible, right? It's not close to 0, but it's definitely not above 0.85, okay? And then it says, using this information, predict what would happen in 2018, right? What's happening in 2018? Well, 2018 would be year 24, right? So all you're going to do is you're going to put 24 in for x. So you're going to do 0.16 times 24 plus 6.5, right? And you can use a calculator for that. I've got one off to the side, but you can just, multiply that out however you want to multiply that. I don't care how you do that. That's not what this lesson's about. So 0.16 times 24 plus 6.5 comes out to 10.34, right? So predict the number of metals. We would predict about 10.34 metals. So we would predict in 2018 that there would be about 10.34 metals. If you actually look at the data that year, in actually 2018, we actually had 9 metals, right? Just like the other following 2 Winter Olympics. So we're close, right? Our prediction said around 10 and we got 9. The reason that we're off a little bit is because, that's reality, right? Things happen. It's not always going to be a straight line or anything like that. So that's all you're doing. So if based on this data, you would predict that there'd be around 10.3 metals, so around 10 metals would be given, right? And how confident are you that that's how many it would be? Since your correlation coefficient was kind of low, a little bit low, you're kind of, it's going to be close to that, maybe not exactly that, right? So 9 was a good fit. All right. Next question. Below is a table showing the U.S. Federal Reserve prime interest rate on June 1st of various years. Find a linear regression for the prime rate as a function of the number of years since 2002. Now, if you're sitting in my class, I'm going to have this big, long conversation about what the prime interest rate was. It's actually kind of interesting. But I'm going to talk about this real quick, a brief what the prime interest rate is. The prime interest rate is the Federal Reserve, the U.S. government. If one bank wants to lend money to another bank, and there's lots of reasons they want to do that, right? If one bank wants to lend money to another bank, they have to pay them back their money plus interest, right? And the amount of interest that they have to pay them back is the prime interest rate, right? So in 2002, if one bank wanted to let another bank borrow money, they would let them borrow the money, but they would also charge them, right? They would also charge them 4.75% interest per year, right? All right. So that's what the prime interest rate is. It's just the percent of interest that banks have to charge each other when they lend money, right? Just looking at this data real quick, it's kind of neat. If you actually started looking at it, you would notice that, look, in 2002, it was 4, it went up to 8, 5, and then it nosedived for a very long time, right? So the first thing I want to talk about, if you're in my class, we're going to spend a long time on this, but why did it go up and then it plummeted for many, many years? You know what happened? There was a recession, right? The U.S. economy was doing terrible. This was when the 2010, during that time, is when the housing market collapsed, right? When all the banks were doing terrible, people were losing their jobs and everything else. So when the country's not doing good, right? When the countries are not doing good, the U.S. government will bring down the prime interest rate so that they can borrow money from each other cheaper. If the interest rate is really high, like in 2006, they're not going to borrow money, right? Because if they borrowed money, they're charging 8% interest, so they don't want to do that. So, right around here, if you start looking at the data, right around there is when the housing market collapsed and all those, Goldman Sachs went out of business and lots of things happened. If you ever have a chance, go watch the movie or read the book, even better, The Big Short, right? It's about the collapse of the U.S. economy because of that housing market, right? Basically, I'll give you the 2-second version. Banks were letting people buy houses that did not have the money or the ability to pay for those houses. So all these people were buying houses, but they couldn't pay for those houses. And then what happened was all these people couldn't pay for their houses. So the banks got the houses back and they lost tons of money when that happened, right? When they foreclosed. So that's what happened, right? Around 2010, it crashed. And then slowly but surely, the economy recovered. And by 2018, the prime interest rate was back up pretty decently, right? All right. So that's the data. So it says, find a linear regression, right? We're reading this here. Find the linear regression for the prime interest rate as a function of number of years since 2002. Okay, so 2002 is year 0. 2004 is year 2, 4, 6, 8, 10, 12, 14, 16. Right? So what we're going to do is, let's do the rest. Independent variable. The years since 2004, right? The dependent variable, the prime interest rate. And that's a percent, right? All right, so let's go do this. Remember what we're going to do, just like before. Menu 6, we're going to doc B, that'll clear our calculator. Doc B clears the calculator. Then do menu 6, 1, 4. Open up a set, put in the x values, and if we look once again, our x values were from 0 to 16. So we're going to write those. 0, 2, 4, 6, 8, 10, 12, 14, and 16, right? I think I got them all. Let's make sure. Yeah. 4.75, 4.25. So now we're going to do the y's, right? 4.75, 4.25. All I'm doing is just typing all these in. So I don't have it in front of me. So 8.255 and so 8.25, 5. What's next? And then for the next 3 years, right, 3.25. So the next 3 times is 3.25. So 3.25, 3.25, 3.25. What do we got? 3.75 and 5 again, right? So then 3.75 and then 5 again, right? And what I would do, since I did so many, I would count how many numbers are here. So 1, 2, 3, there's 4 numbers. 4, right? 5, 6, 7, 8, 9. I think there's 10 numbers there. I'd have to count again if I'm not sure. But if I look here, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So I'd have to go back and make sure I have 9 numbers. If you count them, I'm pretty sure I'm right, but there's 9 numbers in the x values and there's 9 numbers in the y values. So press OK. And there it is, right? This. Oh, okay, this is cool. I just made a mistake, and that's actually good that I made the mistake. Listen, I didn't do menu 613. I did menu 612. And all it did is reversed it, right? It says in the form of a plus bx. I want it to be mx plus b, so the b is my slope and the a is my y-intercept. So if you ever screw that up, that's okay. That's not a big deal, right? So a is 5.3 and the y and b is negative 0.1. So this is the slope in this case. So the slope is negative 10, right? I'm going to write that down. The slope is negative 0.10 or 10 hundredths, right? And the y-intercept is 5.34. 5.34. So the equation is negative 0.10 x plus 5.34, right? Look at the correlation coefficient. This is kind of interesting, right? It looked like the interest rate was going up and then coming down. If you were to graph this, it's going to go up and then come down. It's going to look like this. And that's, if you started graphing those points, it's going to start looking like a curved line like this. That's probably not going to be linear. It's probably not going to fit a line very well. So I would expect the R value to not be close to 1 or negative 1. So let's see if I'm right. Was the R value close to 1 or negative 1? No, it was not even close, right? Remember what we said, if this R value is above 0.85 or negative 0.85, it's good fit. This is a terrible fit. The correlation coefficient is negative 0.35, right? The correlation coefficient is negative 0.35. Is that a good fit? No. What is this saying? Since the correlation coefficient is so close to 0, it's saying that this data does not look like a straight line. Why is that true? Because the economy is not based on linear equations. The economy has got so many factors that it's not going to be based on a straight line. You know, there's too many things going on. So it's not a straight line. It's not linear. All right? So that's what it's saying. Predict the prime interest rate in 2019. Now, because our correlation coefficient is so low, our prediction is probably not going to be accurate. Okay? But if I want to do 2019, that is what? That is year 17, right? That is year 17. So all I would do is I would go and rewrite the equation using that. So y equals, sorry, I'm going to, negative 0.10 times 17 plus 5.34, right? So I would just type that in, right? I guess I can do it on my own calculator. I have a calculator off to the side here too. So I'm just going to do it there because you don't need to see that. You're just going to type that in, not a big deal. So negative 0.1 times 17 plus 5.34, we get 3.64, right? We get 3.64, right? And if you actually looked at the prime interest rate in 2019, it's actually pretty close to 5, right? So we weren't close at all. Why? Because the correlation coefficient was telling us this is not linear, so our prediction's probably not going to be very good. Okay. Well, that's it, guys. That's a linear regression, right? And that's taking that information and making sense of it. Okay. All you're going to be doing, right, is taking some data and turning it into XY coordinates, going into an Inspire, doing menu 613, right? 6, 1. And if you happen to hit 614, which is a plus bx, and you meant mx plus b, you can always fix it, right? Just before I go, you can also do quadratic regressions if you think it's based on a quadratic equation or cubic or quartic or power or exponential. You can do all kinds of different types of regressions, right? So there you have it. Not hard. By this point, you should be pretty good with this kind of stuff. And if you need help, send me an email to mathninjavideos@gmail.com, or leave me a comment on my website and I'll get back to you. All right, good luck with this. Bye.